What is the most powerful thing in the universe? There are monsters out there, looking in the dark. For centuries, astronomers scanned the heavens again and again, without ever spying them. But behind the familiar stars and nearby calm galaxies of our universe lay something far more vicious, far terrible, far more powerful, complete invisible to the human eye. You would never see them even on the darkest of nights. Indeed, at first, they appeared as nothing but distant, dim pinpricks of strange radio emission. But those pinpricks revealed something no astronomer could have ever expected, something so strange, so bizarre, that for years nobody even believed that they could exist, that there must have been some mistake in our observations. Thankfully none, for if they were any closer, they would flood us, our galaxy, our solar system, our planet with deadly radiation. A single one of these monsters can easily out over 1040 joules every second. For comparison, our sun outputs about 1034 joules, 1,000,000 times less every year. The brightest among them outshine stars, outshine galaxies, outshine 1,000 galaxies at once. Some extreme events, like the most powerful supernovae, can briefly become brighter than these beacons. But those events are temporary, ephemeral, flaring and dimming in a matter of weeks. When these monsters awake, they stay powered for millions of years. In just a fraction of their lifetime, they can easily produce more energy than even the most intense cosmic explosions. And they are hungry. They feed on anything, and are capable of tearing apart entire stars in a single fit of rage, producing flashes of radiation and jets of charged particles that shoot out from millions of light-years, piercing through galaxies and spreading their destruction throughout entire clusters. They are the quasars, the most powerful engines in the known universe. But what drives these engines? What powers these lighthouses in the deep? The answer will take us on a journey through some of the most extreme physics in the universe, and even provide us with a grim warning. For though our galaxy is quit now, it will not stay that way forever. The most distant quasar from us is 13 billion light-years away. It would take nearly the entire history of the universe to travel to, and that is without the universe expanding at the same time. Space is big and getting bigger, and sometimes that can make us feel small. The impossible lights. At first, astronomers had no idea what they were seeing. By the 1950s, science had grown used to the idea of galaxies outside of the Milky Way, but even in this expanded cosmological view, the belief was that our universe was relatively small, only a few billion light-years across at most. And that expanded cosmos seemed relatively simple, even boring. There were galaxies, there were clusters of galaxies, there were vast expanses of nothingness. For a time, astronomers were able to convince themselves that they were finally starting to figure things out. But in the mid-20th century, there was a technological revolution. Optical telescopes, capable of seeing objects in visible wavelengths of light, were becoming enormous. And our ability to use the rest of the electromagnetic spectrum, wavelengths of light outside the visible, grew along with that. And with those new observations came realization that the universe was far weirder than we could have ever imagined. One of the first revolutions was in radio. In the 1930s, the pioneering engineer Carl Jansky solved the problem of how to reduce noise in sensitive radio antennae and discovered the first radio signals coming from deep space. Among the many bright and obvious sources, like Jupiter, the Crab Nebula, and nearby galaxies, astronomers also discovered numerous small, faint, distant point-like radio objects. These strange objects appeared all over the sky, emitted radio waves at a broad range of wavelengths, and could not be seen with visible or infrared telescopes. The only clue they gave was their position. They appeared both within the band of the Milky Way and outside of it. Since our galaxy is a thin disk, this meant that the source had to either be extremely close, like the visible stars of the night sky, or extremely far away, like the distant galaxies. But if they were close, we have been able to also see them in optical wavelengths. And if they were extremely far away, their intensity in radio wavelengths implied they were the brightest objects in the entire universe. Understandably, many astronomers pushed back against this interpretation, not only arguing about their distance, but also openly questioning what could possibly power something that bright. Finally, a breakthrough came in 1962. By the 1960s, astronomers had been able to refine the techniques of radio astronomy to the point they could more precisely measure the location on the sky of these strange sources. With these new techniques, astronomers Cyril Hazard and John Bolton found that one radio source, known as 3C273, would undergo occultations of the Moon, allowing them to provide an extremely accurate estimate of its position. Following up on that work, the Dutch-American astronomer Maarten Schmidt discovered a faint object in the same location in the visible spectrum of light. Within that visible light, Schmidt found the usual collection of bright spectral lines and dark gaps, the fingerprints of elements and molecules found throughout the cosmos. But these lines were not in their usual wavelengths. Instead, they were shifted towards the red end of the spectrum by nearly 16%. To get that kind of redshifting, either 3C273 had to be moving away from us at an incredibly fast speed, or it had to be incredibly far away. By this time, astronomers had been slowly accepting the Big Bang theory of the universe, the view by that the cosmos was once smaller in the past, and is continuing to grow in the present day. Under cosmological expansion, light from distant objects redshifts because the space between them and us expands, stretching the light out into longer wavelengths. And when he interpreted the redshifting of the light from 3C273, Schmidt realized it Saturday, 3rd April billion light-years away. It was the most distant object, by an order or magnitude, ever observed. In 1966, Time magazine put Maarten Schmidt on its cover, comparing the magnitude of his discovery to those of Galileo, saying, "The 17th-century Italian started scientists and theologians like. The 20th-century Dutchman has had an equally jarring effect on his own contemporaries." 3C273 was a revolution. It is so distant that it appears to us as simply a point-like object of incredible luminosity, in fact making it another record breaker. It was also the brightest known object in astronomy at the time. Stranger still, 3C273 was remarkably compact. Now knowing the location of the object, astronomers dug back through archival photographic plates and found that earlier generations of astronomers had already seen it, without recognizing it for what it was. Year after year, 3C273 had shown up, but its brightness had varied between annual observations. To change brightness within a year, an object must be smaller than a light-year across, because any changes to the object can only propagate at a speed lower than the speed of light. So not only was 3C273 far brighter and far more distant than any known object, it managed to accomplish both these feats in a volume smaller than our solar system. With this technique of matching radio sources to visible light objects in place, astronomers went on to confirm the distances to dozens of these so-called quasi-stellar radio sources, the name coming about as early astronomers knew that these objects were not normal stars, but had absolutely no clue what they could actually be. It was in 1964 that the astrophysicist Honghe Qiu coined its modern, catchier name in the journal Physics Today. So far, the clumsily long name, quasi-stellar radio sources, for convenience, the abbreviated form, quasar, will be used throughout this paper. And so, the quasar was born. The debate over the true nature of quasars raged for decades within the astronomical community. Many astronomers believed that the original interpretation was correct, that were incredibly bright, incredibly compact, and incredibly distant objects. but they could not explain what powered these extreme objects. Others continued to argue that these were some sort of exotic star, much closer to our own galaxy, that provided such an extreme amount of gravitational pull that light escaping from them would redshift, making them appear much more distant than they really were. But it wasn't one decisive measurement that cemented the cosmological nature of quasars, but rather a gradual of observational pressure which grew hand in hand with the acceptance of the Big Bang. The Big Bang theory tells us that the universe changes with time. Not only was it smaller in the past, it was also different. Quasars only appear in the extremely distant universe. Indeed, the nearest quasar sits over 700 million light-years away. Since astronomy acts like a time machine, with more distant observations revealing the nature of younger universe, these observations tell us that quasars were only active in the distant past and have now gone quiet. This idea fits perfectly with the Big Bang, because we expect the universe to change as it revolves with time. Our dawning understanding of the age and size of the universe helped paint a portrait of a gigantic, ancient cosmos that could easily accommodate the distances to even the most far-flung quasar. And so, astronomers were left with little choice. They had to accept that these strange, intense objects were truly far away and truly, bizarrely bright. As news of the discovery of quasars worked its way from purely astronomical circles and into the popular imagination, public interest skyrocketed, with writers using the term to elicit a sense of strangeness and remoteness. Meanwhile, astronomers discovered more and more quasars, including ones that were both unusually bright and oddly dim. The very brightest ones got a new name, blazars, while others weren't emitting any radio waves at all, but were somehow extremely bright in X-ray radiation. As radio astronomy became sophisticated, astronomers were able to capture smaller, finer details. The most famous example was Cygnus A, one of the brightest radio objects in the entire sky. Initially thought to be an exotic radio star when it was first discovered, by the 1950s astronomers realized it was far stranger. The central core of Cygnus A was a galaxy, but extending hundreds of thousands of light-years away from that core were two thin, long jets, ending in gigantic bubbles screaming in radio emission. All of these strange objects, whether loud or quiet in the radio, whether relatively nearby or extremely distant, shared one thing in common. Their cores were abnormally bright. In some case, the nuclei of the galaxies outshone all the hundreds of billions of stars within the galaxies themselves. The brightest of the cores indicated an enormous amount of activity of unknown origin. Without knowing the true explanation, astronomers conceived of a brand new term to encompass them all: active galactic nuclei. And so, what was going on in the cores of these galaxies? Why were some the most luminous objects in the universe, while others were relatively quiet? What generated the radio emissions, and why did some blast out X-ray radiation? Astronomers had discovered a zoo of active galaxies throughout the cosmos, with a dizzying and confusing array of galactic creatures. Something must power them. Something must generate the energies needed to make the brightest of them outshine 1,000 galaxies at once. Something must enable them to be seen from the distant reaches of the far universe. These active galactic nuclei must have something in common, and it was clear that something lived in their cores. And so understand what drives these, the most powerful engines in the known universe, we have to look a little closer to home. We have to visit the core of our own Milky Way galaxy.